I bet you didn't know just how many myths surround humanity's greatest journey into the cosmos. Welcome to Planet Pulse, the channel where we dive deep into the mysteries of space, unravel the science behind the headlines, and bring you the most fascinating stories from the universe. If you're passionate about space exploration, cosmic discoveries, and the real science that powers our understanding of the universe, you're in the right place. Today, we're taking on the legendary Voyager spacecraft. Twin probes, launched into the cosmic dark nearly half a century ago, now the stuff of space legend. We've all heard the stories, that Voyager was built to be our first emissary to the stars, that it was the first venture into the great unknown beyond the planets, and that even now, it sends back crystal-clear images from interstellar space. The narrative is compelling, a testament to human ingenuity and our relentless desire to explore. It's a story of pioneers charting a course into the void, carrying a golden record, a message in a bottle for any cosmic neighbors who might find it. But what if I told you that much of this popular story, the one that has captured our collective imagination, is woven with threads of myth? What if the reality of the Voyager mission is even more fascinating, more complex and more profound than the legends suggest? The truth isn't about diminishing their achievement, but about appreciating the real, breathtaking story of their journey. These are just some of the myths many people believe about the Voyager spacecraft, but would you believe that none of these claims are true? In this video, we'll show you the 7 most popular myths people believe about the Voyager space probes, and the truth about them. Let's begin. Our journey today isn't just about debunking myths, it's about rediscovering a mission that redefined our understanding of the solar system and our place within it. We'll travel back in time to their conception, fly by gas giants with them, and venture into the tenuous boundary that separates our sun's influence from the vast interstellar ocean. We will separate the science fiction from the scientific fact, and in doing so, we'll gain a deeper appreciation for one of the greatest exploratory missions ever undertaken by humankind. The universe is full of wonders, and the truth is often the most wondrous story of all. There's a romantic notion that the Voyager probes were conceived from the very beginning as humanity's first messengers to the stars. We picture brilliant minds at NASA in the 1970s, gazing at star charts and designing these robotic explorers with the explicit goal of leaving our solar system behind forever. It's a powerful image, a grand, ambitious plan to send a piece of ourselves, a whisper of our existence, into the cosmic wilderness. The golden record, that beautiful summary of Earth's life and culture, seems to be the ultimate proof of this interstellar intent, a calling card for distant civilizations. But the universe, and the history of space exploration, is often a story of serendipity and evolving purpose. The primary original mission of Voyager 1 and Voyager 2 was not, in fact, to journey to the stars. It was to conduct a grand tour of our own cosmic backyard. The engineers and scientists had noticed a rare alignment of the outer planets, Jupiter, Saturn, Uranus, and Neptune, that occurs only once every 176 years. This celestial syzygy was an unmissable opportunity, a gravitational slingshot waiting to be used. The plan was to use the immense gravity of each planet to bend the spacecraft's trajectory and fling it toward the next one, like a cosmic game of pinball. This technique, known as a gravity assist, would save immense amounts of fuel and time, allowing a single mission to visit multiple worlds. The focus was squarely on these gas and ice giants, mysterious worlds we had only glimpsed through telescopes. The mission was about planetary science, about understanding the atmospheres, rings and moons of our own solar system. So, the Voyagers were first and foremost planetary explorers. Their mission was to conduct an unprecedented close-up reconnaissance of the outer solar system. They were designed to survive the intense radiation belts of Jupiter, to analyze the magnificent rings of Saturn, and, if all went well, to push onward to the enigmatic distant worlds of Uranus and Neptune. Their instruments were built to measure magnetic fields, charged particles, and to capture images of cloud tops and alien moons. It was only after these tasks were spectacularly accomplished that the mission's next chapter was written. The gravity assist that propelled them from planet to planet had also placed them on an escape trajectory, a path leading out of the solar system. With their planetary objectives complete, NASA officially renamed the mission the Voyager Interstellar Mission. It was an extension, a brilliant and opportunistic repurposing of 2 spacecraft that had already exceeded every expectation. Think about that. The journey into interstellar space was not the original blueprint. It was the magnificent encore to a performance that had already brought the house down. It speaks to the ingenuity of the mission planners, who saw a chance to do something more, to push the boundaries not just of our solar system, but of exploration itself. The probes weren't failures if they didn't reach the stars. They were already triumphs. This shift in focus highlights a crucial aspect of scientific exploration. You seize the opportunities the universe presents. The Grand Tour was the opportunity of a lifetime, and the subsequent interstellar journey was the unexpected, yet profound bonus. The Voyagers became interstellar emissaries by virtue of their success, not by their initial design. Their legacy is a testament to both meticulous planning and the beauty of embracing an unforeseen path. And so, the myth of a purely interstellar purpose gives way to a more nuanced, and I think more inspiring truth. It's a story of a mission that grew in ambition as it traveled, a mission that began by looking at our neighbors and ended by looking out into the vast, open expanse of the Milky Way galaxy. The Voyagers teach us that sometimes the greatest journeys are the ones whose destinations are discovered along the way. In the popular narrative of space exploration, the Voyager probes are often hailed as the ultimate pioneers, the very first human-made objects to leave the planetary bounds of our solar system and venture into the great unknown. It's a compelling title, the first. It evokes images of Lewis and Clark, of Magellan, of those who step into uncharted territory before all others. We imagine Voyager 1 piercing the veil of the solar system, a lone sentinel crossing a boundary no machine had ever crossed before it. However, the history books of space tell a slightly different story. The honor of being the first to journey beyond the orbit of the farthest known planet at the time, Neptune, and head towards the edge of the sun's influence, doesn't belong to the Voyagers. That distinction, that pioneering first step, was actually taken by their predecessors, two quieter but no less remarkable probes named Pioneer 10 and Pioneer 11. They were the true trailblazers in this regard. Launched in 1972 and 1973 respectively, the Pioneer probes were simpler machines, but their mission was audacious. Pioneer 10 was the first spacecraft to traverse the asteroid belt, a region once feared to be an impassable debris field. It was the first to make direct observations of Jupiter, our solar system's largest planet. After its flyby, its trajectory sent it careening outwards, on a path that would eventually take it beyond all the planets. On June 13, 1983, a full 6 years before Voyager 2 would even reach Neptune, Pioneer 10 crossed the orbit of the outermost planet. At that moment, it became the first human-made object to journey beyond the planetary region of our solar system. It was a quiet milestone, perhaps overshadowed by the more advanced Voyager missions that would follow, but it was a monumental achievement. Pioneer 10 was the one that proved the journey was possible. Pioneer 11 followed a similar, albeit different path. After its own encounters with Jupiter and a stunning first-ever flyby of Saturn, it too was flung onto an escape trajectory. It also crossed the planetary frontier, following in the footsteps of its twin. These probes were the scouts, the ones who went ahead to test the waters, facing the unknown radiation and dust of the outer solar system. So why do the Voyagers get so much of the credit? It comes down to a combination of timing, technology, and a bit of cosmic chance. The Voyagers were more sophisticated, carrying a more advanced suite of instruments. They gave us the breathtaking, high-resolution images of the outer planets and their moons that are etched into our collective memory. Their Grand Tour was a far more complex and photogenic mission. Furthermore, the Voyagers are the spacecraft that have actually crossed the heliopause, the boundary where the sun's solar wind is turned back by the interstellar medium. While Pioneer 10 was the first to leave the planetary region, Voyager 1 was the first to enter interstellar space itself, a different and more distant milestone. We'll talk more about that distinction later. Sadly, we lost contact with Pioneer 10 in 2003, so we don't know if it has crossed that same boundary yet. Understanding the role of the Pioneer probes doesn't diminish the Voyager legacy. Instead, it places it in its proper context, as the culmination of a series of exploratory steps, each one building on the last. Science is a collaborative, multi-generational effort. The pioneers walked so the Voyagers could run. They were the vanguard, and their quiet journey into the dark paved the way for the spectacular success that followed. We carry this beautiful image in our minds, the Voyager probes, our lonely explorers in the dark still acting as our eyes in deep space. We imagine them dutifully snapping pictures of nebulae, distant stars, and perhaps even the ghostly glow of the interstellar medium, beaming these images back to us in real time. It's a science fiction dream come true, a live feed from another star system, a constant stream of visual wonders from the void. The idea that we are still seeing through Voyager's cameras is incredibly powerful, but the reality is, the cameras on both Voyager 1 and Voyager 2 went dark a long time ago. Their final photographic assignment was one of the most poignant in the history of exploration. In 1990, after Voyager 1 had passed the orbits of all the planets at the urging of the great astronomer Carl Sagan, NASA commanded the probe to turn its camera around one last time. It was to take a final look back at the home it was leaving forever. The result was the iconic family portrait of our solar system, including the famous image known as the pale blue dot. It shows Earth as a tiny, almost insignificant speck of light, suspended in a sunbeam, a humbling perspective on our place in the cosmos. After capturing this profound farewell image to conserve precious power and memory for the long interstellar journey ahead, the cameras on both spacecraft were permanently switched off. There was simply nothing left for them to photograph at a resolution that would be meaningful. So, for over 3 decades the Voyagers have been flying blind. Their mission is no longer about sight in the way we typically understand it. They are now feeling their way through the universe, not seeing it. Their remaining active instruments are designed to measure the environment around them. Things like magnetic fields, cosmic rays, plasma density, and charged particles. They are our sense of touch and hearing in interstellar space, reporting on the conditions of this unexplored territory. Furthermore, the idea of real-time communication is a casualty of cosmic distances. Light, the fastest thing in the universe, takes time to travel. As I speak, Voyager 1 is over 24 billion kilometers or more than 15 billion miles away. A radio signal, traveling at the speed of light, takes over 22 hours to make the one-way trip from the spacecraft to Earth. A command sent from Earth takes another 22 hours to reach the probe. This means a simple conversation with Voyager 1 has a round-trip time of nearly 2 full days. This is not a live feed. It is a slow, deliberate, and patient exchange of information. The data trickles back at an incredibly slow rate, just 160 bits per second, far slower than the dial-up modems of the 1990s. Scientists must wait patiently for this precious data to be collected by the massive dishes of the Deep Space Network. This delay profoundly changes our relationship with the probes. We can't react instantly to what they find. We must send our commands and then wait, hoping they are received and executed correctly. Every packet of data received is a victory, a faint whisper from an immense distance, a message that has traveled for nearly a day just to reach us. So, while the Voyagers are still communicating, they are not our visual correspondents. They are scientific scouts sampling an alien environment and sending back their findings in a language of fields and particles. The romance of real-time images has been replaced by the stark, beautiful reality of collecting scientific data from a place no human instrument has ever been, a process that requires immense patience and technological prowess. When news broke in 2012 that Voyager 1 had entered interstellar space, it was a moment of global celebration. Headlines declared that humanity had left the solar system. It's an easy and honestly pretty exciting conclusion to draw. The probe had crossed the heliopause, the turbulent boundary where the stream of charged particles from our sun, the solar wind, is finally stopped by the pressure of the interstellar medium. It sounds like a definitive exit, like crossing a national border, or stepping out of your front door. But the solar system is a much bigger, much messier, and much more mysterious place than we often imagine. Crossing the heliopause is an incredible milestone, to be sure. It means Voyager 1 is no longer bathing in the sun's atmosphere. It is now, for the first time, flying through the medium between the stars. It is sampling matter that originated from distant, ancient supernova explosions. This is without question interstellar space. However, leaving the sun's atmosphere is not the same as leaving the sun's gravitational kingdom. The solar system, defined by the gravitational influence of our star, extends vastly farther than the heliopause. The true outer boundary of our solar system is a theoretical, immense sphere of icy bodies known as the Oort cloud. This is the reservoir of comets, the sun's most distant and loosely held family members. To put this into perspective, Voyager 1 is currently traveling at about 38,000 miles per hour. It took over 35 years to reach the heliopause. At its current speed, it would take Voyager 1 approximately 300 years just to reach the inner edge of the Oort cloud, and the cloud itself is thought to be so vast that it would take the spacecraft another 30,000 years to fly through it and emerge on the other side. Think about that for a moment. 30,000 years. That is a span of time longer than all of recorded human history. The pyramids of Giza were built about 4,500 years ago. The first cave paintings are about 40,000 years old. The journey through the sun's ultimate frontier, the Oort cloud, is a journey on a truly geological, almost unimaginable timescale. Only after completing that epic trek could Voyager 1 be said to have truly left the solar system. So, we must be precise with our language, as science demands. Voyager 1 has left the heliosphere, the bubble blown by our sun. It has entered interstellar space. But it has not yet left the solar system. It is flying through the vast, empty foyer of the sun's gravitational house, having only just stepped out of the inner rooms. It is still very much a part of our cosmic home, bound by the sun's gravity. This distinction isn't just pedantic, it gives us a profound sense of scale. It teaches us that our solar system is not just the tidy collection of 8 planets we learn about in school. It is a colossal structure dominated by the gravity of a single star, extending its influence across a mind-bogglingly huge volume of space. The heliopause is just one border in a series of nested frontiers. The journey of Voyager 1 redefines our very concept of here. It shows us that leaving home is a long, long process. The probe has taken the first crucial step into a larger environment, the galactic neighborhood, but it will be a deep future descendant of humanity, if any, that will be around to mark the moment when it finally clears the last gravitational vestiges of its home star. When you think about the fastest thing humanity has ever built, the Voyager probes often come to mind. They are hurtling away from us at incredible speeds, covering millions of miles every single day. Voyager 1, for instance, is traveling at over 38,000 miles per hour, or about 17 kilometers per second. To our terrestrial sensibilities, that speed is staggering. It's fast enough to circle the Earth in about 40 minutes. Surely, this must be the speed record for a human-made object. This belief is understandable. The Voyager's journey is the longest, and their distance from us is the greatest. It seems logical to connect that distance with unparalleled speed. For a long time, they were indeed among the fastest objects we had ever launched. Their velocity is a testament to the powerful rockets that launched them and the clever gravitational assists they received from the gas giants, which acted like cosmic slingshots. However, the title of fastest spacecraft ever belongs to a different, more recent explorer. That honor goes to the Parker Solar Probe. This daring mission, launched in 2018, has a very different objective than Voyager. Instead of flying away from the sun, the Parker Solar Probe is designed to fly directly into our star's outer atmosphere, the corona, to study it up close. To do this, it performs a series of ever closer flybys of the sun. And as it gets closer to the sun, the star's immense gravity takes hold, accelerating the probe to truly mind-bending velocities. According to the laws of orbital mechanics, discovered by Johannes Kepler centuries ago, an object moves fastest when it is closest to the body it is orbiting. During its close approaches to the sun, the Parker Solar Probe has already shattered every speed record set by Voyager. In late 2021, the Parker Solar Probe reached a speed of over 364,660 miles per hour, or about 101 miles per second. That's nearly 10 times faster than Voyager 1. Let me say that again, 10 times faster. And it's not done. With each successive orbit, it will get closer to the sun and move even faster. It's projected to eventually reach a top speed of around 430,000 miles per hour. At that speed, you could travel from New York to Los Angeles in about 20 seconds. There have been other spacecraft like the Helios probes in the 1970s and the Juno probe currently at Jupiter that have also achieved speeds greater than Voyager's at certain points in their orbits. Speed in space is often relative and temporary, a function of where you are in a gravitational field. The Voyager's speed is impressive, because it is a constant, sustained escape velocity, carrying them ever outward, but the raw record for peak velocity belongs squarely to the Parker Solar Probe. Its mission is a dance with gravity, a series of daring swoops into the sun's fiery embrace, each one faster than the last. It's a different kind of exploration, not about distance, but about proximity to an extreme environment. So, we must update our cosmic record books. The Voyagers are the most distant human-made objects, our farthest emissaries, but they are not our fastest. That title belongs to the intrepid solar explorer, a probe that teaches us that to achieve the greatest speeds, you don't run away from a star, you run towards it. It's a beautiful paradox of celestial mechanics. In our daily lives and in much of our space exploration, we are accustomed to one primary source of power, the sun. We see images of the International Space Station with its huge, glittering solar arrays. We see the Mars rovers, like Spirit and Opportunity, adorned with solar panels to drink in the faint Martian sunlight. It's natural to project this familiar technology onto all spacecraft, including the Voyagers. The image of two probes with vast solar wings gliding through the darkness is a common one. But, for a mission to the outer solar system and beyond, solar panels are simply not an option. The sun's energy follows what we call the inverse square law. This means that as you double your distance from a light source, the energy you receive from it drops to 1/4. By the time you get to Jupiter, which is 5 times farther from the sun than Earth, the sunlight is only 1/25 as intense. At Saturn, it's about 1/100th. By the time you reach Neptune, 30 times Earth's distance, the sunlight is 900 times weaker. Out in the frigid twilight of the outer solar system, and certainly in the absolute darkness of interstellar space, solar panels, large enough to power a spacecraft, would have to be the size of football fields. It's completely impractical. The Voyager's engineers knew this from the beginning. They needed a power source that was compact, reliable, and completely independent of the sun. They needed something that would keep the probes warm and working for decades. The solution they chose is a marvel of nuclear engineering called a radioisotope thermoelectric generator, or RTG. This is not a nuclear reactor like you'd find in a power plant or a submarine. There are no chain reactions, no control rods, no moving parts. The principle is elegantly simple. The RTG contains pellets of a radioactive material, in this case, plutonium-238. As this plutonium naturally decays, it releases a steady, predictable amount of heat. This heat is then converted directly into electricity. The RTGs use a device called a thermocouple, which is a junction of two different metals. When one side of the junction is heated and the other side is kept cool by the cold of space, a small electric voltage is produced. By arranging many of these thermocouples around the hot plutonium core, the RTG can generate a consistent, albeit small supply of electrical power. At launch, the 3 RTGs on each Voyager probe produced about 470 watts of power, enough to run a few bright light bulbs. But the beauty of this system is its longevity. The half-life of plutonium-238 is about 88 years. This means that every year, the power output drops by a tiny, predictable amount, about 0.8%. This slow, graceful decline in power is what has allowed the Voyagers to continue operating for nearly half a century. So, the Voyagers are not solar-powered. They are nuclear-powered. They carry their own internal source of energy, a slow-burning fire that has kept them alive through the cold and dark. It is this nuclear heartbeat that allows them to continue sending their faint whispers back to us from beyond the heliopause. It's a technology that is essential for exploring the dim outer reaches of our solar system and the interstellar void that lies beyond. This fact is a powerful reminder that exploration often requires us to move beyond our familiar methods. To journey far from our star, we had to learn how to carry a small piece of a different kind of star with us, the slow, steady, and enduring energy locked within the heart of an atom. The sheer longevity of the Voyager mission is astounding. Launched in 1977, these machines have outlasted their original design life by decades. They've survived the harsh radiation of Jupiter, the cold of deep space, and have continued to function, sending back precious data. This incredible endurance leads to a hopeful myth that the Voyagers can continue their scientific mission for many more decades, that our connection to them is secure for the foreseeable future. We want to believe that these faithful servants will keep reporting back from the interstellar frontier for as long as we can listen. The idea of them falling silent is a sad one, like saying goodbye to an old and trusted friend. We have known them our entire lives, and it's hard to imagine a time when they are no longer phoning home. Their journey seems so eternal that we assume their ability to communicate is as well. Unfortunately, the laws of physics are relentless, and the Voyagers are running out of time. The culprit is their power source, the very RTGs that have kept them alive for so long. As we discussed, the plutonium-238 that powers them decays, and their electrical output has been steadily dropping since launch. As of today, the power budget on each spacecraft is critically low. The mission engineers at NASA have been performing a masterful, delicate balancing act for years to keep them alive. To conserve the dwindling power, they have been systematically shutting down non-essential systems. The first to go were the cameras back in 1990. Since then, heaters for various instruments have been turned off, one by one. The engineers take calculated risks, allowing some components to operate at temperatures far colder than they were ever designed for. Each time an instrument survives being switched back on after a deep freeze, it's a small miracle. But this process cannot go on forever. The probes need a minimum amount of power just to run their core systems, the computer, the transmitter, and a few essential heaters. Soon, there will not be enough power to run even a single scientific instrument. The team at NASA's Jet Propulsion Laboratory estimates that they will need to start turning off the final scientific instruments around the year 2025. By sometime around 2026, or perhaps a bit later if they get lucky, there will simply not be enough electricity to keep the radio transmitter operating. At that point, the Voyagers will fall silent forever. Their whispers from interstellar space will cease. Their journey will continue, but their conversation with their creators will be over. They will become true ghost ships, sailing on through the Milky Way in silence and darkness. This is not a failure. It is the inevitable final chapter of an overwhelmingly successful mission. To have operated for nearly 50 years in deep space is a record that may never be broken. The end of the mission is a poignant reminder that even our most enduring creations are finite. It gives us a deadline, a reason to cherish every last bit of data they send back in their final years. Their impending silence adds a new layer of meaning to their journey. Soon, their only function will be the one they acquired by chance, to be messengers. They will silently carry their golden records through the galaxy, perhaps for billions of years. Their scientific mission will end, but their cultural mission, their role as artifacts of a curious and hopeful civilization, will have only just begun. So, the Voyagers are not what we thought they were. They were planetary explorers who became interstellar pioneers by chance. They weren't the first to cross the planetary boundary, but they were the first to touch the space between the stars. They fly blind and speak to us across a gulf of time and space, powered by a nuclear heartbeat that is slowly fading. Their story is more complex, more constrained by reality, and ultimately, more human than the myths suggest. Knowing the truth doesn't diminish their grandeur, it enhances it. It transforms them from science fiction icons into monuments of real scientific and engineering genius. Their mission, even as it winds down, forces us to confront the immense scales of space and time. Soon, they will fall silent, their scientific purpose concluded. But their journey will go on. They will drift through the Milky Way for eons, long after we are gone, long after the Earth itself has changed beyond recognition. They are our silent, enduring ambassadors to the cosmos, carrying a golden record that sings of a world of oceans, cities, and ideas. They are a testament not just to what we can build, but to what we can dream. This brings us to a final, awe-inspiring thought. The Voyagers are heading in the general direction of other stars, though they aren't aimed at any specific one. But space is vast, and the galaxy is dynamic. Can you imagine this actually happening at some point in the future? What would happen if a civilization from a star near the Sun, like Alpha Centauri, were to find one of the Voyager probes? What would they make of this ancient silent machine and the golden disk it carries? It's a tantalizing question, and the answer is floating out there, waiting in the cosmic dark. If you enjoyed this journey through the mysteries of the Voyager spacecraft, make sure to subscribe to Planet Pulse. Join us for more deep dives into space, science, and the wonders of the cosmos. Hit the bell so you never miss a discovery. The universe is waiting. Let's explore it together.